This is BME Team Number 1 presenting a smart device remote control for fecal emulsification machine. Each member played a key role in the success of our project. Here's a breakdown of member contribution.
Janice was elected team leader and was the main communication line between our mentor and the team. She also played the role as graphic designer and editor, where she compiled and edited the documents during the year. Paul was our materials expert and helped heavily with the physical prototype. He also played the role of secretary during meetings with our mentor. Abid was our SolidWorks specialist and came up with our original design of the remote. Nikita played the role of principal investigator during the research portion of the project. She was our expert on the various design options for the remote. Anthony became interim leader during meetings that Janice could not attend and aided in research investigation as well. Derek's role was to program the interface and answer most of the general questions asked during presentations. All team members played a crucial role in creating the documents throughout the year. Our team works with Abbott Medical Optics in Santa Ana. Every other week we meet with our mentor Kyle Lin to discuss our project. He was vital to the progress of our project, providing guidance and helpful advice throughout the year.
The device that we are working with is AMO's White Star Signature Fecal Emulsification System. The goal of this project is to create an updated version of a remote control for the system that is typically used for cataract surgery. AMO, however, is already one step ahead of the competition. Their two main competitors are Alcon and Bausch & Lomb, who also have similar fecal emulsification machines with remote controls as accessories. However, the main difference between AMO's version and theirs is that Alcon and Bausch & Lomb both use infrared technology to control the machine using the remote. This makes the pairing unidirectional, meaning the remote has to be pointed directly at the sensors on the front of the machine to work. However, the current remote for AMO's White Star is paired using Bluetooth, making the pairing omnidirectional. This means you can use the remote to control the White Star from behind or on the side of the device. The fundamental problem the remote control presents is that it is not intuitive for users. The remote control itself consists only of directional buttons and select buttons, making it difficult to actually navigate through the settings and functions of the White Star system. The controller even lacked labels, so oftentimes the users were not sure what each button's function was. Many users also felt that the remote control was bulky and heavy and did not have a good ergonomic feel. Because of these problems, AMO found that very few nurses were actually using the remote control at all. The basic premise of our design was to create a touchscreen remote that would mimic the interface of the actual White Star system. This way, nurses who had previously used the White Star system would find our remote control intuitive. Initially, we started off with the hopes of having the remote as an application on the iPhone. However, we were concerned that this may lead to non-cognitive errors and other complications.
First steps in our design process was to distribute surveys to get a better sense of the usability issues at hand. In our case, we made 3 different surveys for 3 different types of users. The first survey was designed for nurses. During most cataract surgeries, doctors direct the nurses to adjust and configure the fecal emulsification machine to their specific needs. Thus, nurses are the primary users of the machine and their opinions are essential. The next survey was designed for the technicians. Technicians' opinions towards the device are essential because they are the ones who set up the fecal emulsification machine and pair the remote to the machine. Also, they will be the ones called upon if there are any glitches or malfunctions with the equipment. The third survey we made was defined for marketing personnel. The people who will be marketing the device will be the ones demonstrating the abilities of the device to potential buyers and may have ideas as to make it both aesthetically appealing and more efficient for presentation and sale.
From this feedback, we were able to create a design decision matrix to quantify the options of the remote. These include whether it is wired or wireless, and have a touchscreen or have physical buttons. From taking user needs into consideration, we were able to conclude that wireless and touchscreen are good requirements for our remote control. These requirements and others were laid out in requirement documents.
Requirement documents detail the specific features and functions the product will be able to perform. We wrote out 2 types of requirement documents, a high-level requirement document and a low-level requirement document. The high-level requirement doc tends to be an overview type of document detailing the functions of the product. An example of a high-level requirement would be, the remote shall be rechargeable. Low-level requirements tend to be more specific and detail-oriented when describing the functional capabilities of the product. An example of a low-level requirement would be, the remote shall display the remaining battery life in hours and minutes on the screen. Once we had created our requirement documents, we were ready to move on to the prototyping phase.
During the course of the project, in order for the group to get a better understanding of the overall design of the remote, it was decided to prototype a handheld model. The prototyping process began by detailing hand drawings to meet the group's previously defined specifications for dimensionality. From here, cardboard mock-ups of the size were created. Following this, a final CAD model of the remote was used creating SolidWorks. After finalizing this CAD model, the process of creating the physical model began with purchasing a sheet of raw acrylic. The half-inch thick acrylic was then cut, sandpapered, filleted, and polished before external buttons were fastened.
This physical prototype helps us understand the dimensionality of the device, and alongside this prototype, a working interface was created apart from it to help us get a feel for how the touchscreen would look and function.
The main goal when designing the interface for the remote control was to have it look and act like the touchscreen interface on the White Star Signature machine. This would make it so that doctors and nurses who are already familiar with the machine would not have to learn a completely new interface in order to learn how to use the remote, making it much more likely to be used. Another important goal was to avoid all non-cognitive errors, especially those which could potentially cause harm to the patient. As you can see, the White Star machine has 4 modes which can be used by the doctor: phaco emulsification, irrigation and aspiration, Vitrium, and diathermy. Each mode has its own parameters which can be adjusted during the surgery. Other important parameters throughout the surgery include the IV pole and continuous irrigation mode. The White Star Signature machine already has an option for the doctor to choose and save their own preset settings for the parameters in each mode. Our remote loads these presets upon pairing with the machine and allows the doctor or nurse to choose these presets from the remote quickly. The interface remains simple enough to be navigated easily, but complex enough to control all of the parameters necessary to perform a full surgery.
Because this prototype is more for functionality rather than testing, design options were researched and considered as data for the project. These design options include what material, power source, wireless capability, and touchscreen options a working prototype would have. The following are the results of this research.
The 2 main specs considered for materials are lightweight and drop resistance, and the parameters used for comparison are specific weight and resilience. Compared to the other devices, polycarbonate has the lowest specific weight and high resilience, which would make the remote less heavy as well as more drop resistant. For power source options, nickel cadmium, nickel metal hydride, and lithium ion battery were compared using parameters such as energy density, self-discharge rate, recharge time, amp hour rating, and cost. Lithium ion battery seems to be the most ideal because compared to the other 2 batteries, it has the highest energy density and the lowest self-discharge rate. It is also available in different sizes and shapes, therefore one that fits the design of the device can be easily chosen. After comparing several pros and cons of different touchscreens, we decided that a capacitive touchscreen is best for the device. It has higher selectivity and higher touch resolution than a capacitive touchscreen, which also results in few touch rate errors. 3 different types of wireless options, such as Zigbee, Wi-Fi, and Bluetooth, were compared by listing the advantages and disadvantages. Zigbee has low battery consumption and is usually used for low-level data transfers. Wi-Fi uses the same radio frequency as Bluetooth, but with higher power, resulting in a faster connection and better range from the base station. But it has high power consumption, which can decrease the battery life. Therefore, Bluetooth seems to be the best option because it allows to retain the functions of the remote while not using too much battery.
When trying to get a medical device out into the market, a verification validation protocol is made after the prototyping phase. This protocol details step-by-step procedures to test the requirements listed in the requirement documents. These tests can include leaving the remote on for hours to see how long it takes for it to use up its batteries, or dropping it from a certain height to test its durability. The results of these tests determine whether the product is ready to be sold in the market.
The following is a timeline of the major events that our team went through this year, starting fall quarter to winter quarter and ending with spring quarter.
The current working prototype is unable to communicate with the White Star machine. The next step for this project would be to actually manufacture and implement the remote control for use with the White Star machine.
All in all, our team was able to complete the goals of the project, which included learning about the design process of getting a device out into the market from concept and design to a physical prototype. We were able to learn about understanding user needs from making market surveys. We were able to apply these needs into requirements for our remote control. Then from these requirements, we were able to create a physical prototype from the SolidWorks design. This prototype not only included an acrylic wireframe, but also a working interface through an HTML code. To conclude the design process, we created a validation and verification protocol that is typically used to test the requirements from the previous document. Overall, our team learned valuable lessons like teamwork, diligence, and communication.